Hello everyone. So today we'll continue our topic magnetism and matter. We'll start with the topic the electrostatic analog, and then we'll do Gauss law, and then we will do the first part of the Earth's magnet. I mean like this complete part till here. Then about the magnetization and magnetic density and the magnetic properties of material we'll do in the next class, and then we'll finish this chapter off. It's not much left, it's just this part, and then yeah. Today's is gonna be simple actually. It's gonna be simple. It's just theory, nothing about derivations and all. I mean, even the last one in the last video we studied about bar magnet. Then we covered the magnetic field lines, and then we did bar magnet has an equivalent solenoid. So this topic is kind of important actually. So you just have to know about this, how bar magnet and solenoid were having similarities, and then we studied also about the dipole moment, about torque. So in this we will start from the electrostatic analog. I mean, so this is actually nothing to do with this. Like it means it's basically small. You just have to know about it. So in this, you see it's this much paragraph. So it just says, is the magnetic field, like magnetic field and the electric field, they are similar, okay? So the electrostatic analogy means like things that are different but they have a same common point, okay, like same direction, like example, okay? So like electrostatic, okay, what is electrostatic? Study of charges, which is the first 3 chapters, and then magnetism, which is study of magnets. So they two almost are similar enough. They're almost similar enough, and this is called analog or analogy, okay? So all the equations in this are similar to this. This is what this topic is, this paragraph is all about, this page is all about. That's it. So here it says comparisons between equations. So in this textbook it says comparing the equations 5.2, 5.3, 5.6. So these equations over here, 5.2, 5.3 and 5.6, okay, like this. What is this formula about torque? What is this formula about potential energy? This formula showed us that there is a similarity between electric dipole and magnetic field. This is what we're going to study in this almost small paragraph, I mean page. So the only difference in all the formulas between the electric field and the magnetic field, so the difference between electric field and magnetic field are actually so less. First, here we present electric field as E. This is electric field, and here we represent as B. Remember that. Second, point number 2. Here we care about value of charges, P, which is value of charge, whereas here we take M, which is pole strength. What else is the difference? And the last difference is here there is a constant, right? What is that constant? 1 pi 4 pi epsilon naught, and here the constant is mu 0 by 4 pi. This is the only difference between all the formulas of electric field and all the formulas of magnetic field. Now I'll show you. So these are the conditions. This is this. So we'll just see about this later, okay? This is just simply, in particular, we write down bar magnet, then blah, blah. Okay, this is the main thing. This is the main topic. This is the main importance of our topic. This is all about this. First, this is important, okay? You need to remember this. This is important, okay? This is very, very important. You need to remember this. You can learn one kind of formula about electrostatics, and then you can just use these laws, and then you can convert them into magnetism. Okay, example. What is dipole moment? Means charges due to, net charge due to two charges, positive charge and negative charge. Okay, that is dipole moment. What is it? Here in electrostatics it's P, magnetism it is M. Okay, this is the rule, one rule. Second, here the constant K, constant, oh wait, not constant actually, this 1 by epsilon naught and this is mu naught. This is permeability, which is material material constant, we can say, we can just call it as that, material constant. Okay, now see, first formula we're talking about equatorial field for a short dipole, means the electric field for a short dipole. What is the formula? P 4 pi E naught R cube. Okay, now how about same thing for magnetism? What will it be? Okay, so let's use the rules. What is the rule number 1? P changed into M, we change P into M. Okay, that's first rule. Second, what else do we see? 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. What should we change into? What should mu naught by 4 pi, mu naught by 4 pi, r cube as it is. Okay, I'm saying here the formula is what? Minus P by 4 pi epsilon naught r squared. First, what should I change? P into R, P into M, then M, then, and first it's E over here and it's B over here. First I change A into B, then P into M, P into M, then 4 pi epsilon naught, this I changed to this, epsilon naught 4 pi into R cube. That's it. Now for axial, 2p by 4 pi epsilon 0 r cube. Over here I change P to M, 4 pi epsilon naught to mu naught 4 pi. Now here external, or here torque is what? Pi cross E. Here is what? M cross B. Why? We changed P into M, E into B. Now what is energy? PE, P dot E. Yeah, this is potential energy due to torque. Potential energy due to torque. Minus P dot E. Here is minus MB. You see, that's all in this paragraph. That's all. You don't need to do any derivations. No, nothing. That's all. And then we have about magnetism and Gauss law. So this part, okay, so what is first Gauss law? We'll talk about first Gauss law. What is Gauss law? Gauss law means in a closed surface, the field lines, which is electric or magnet fields, which are going inside, are equal to the magnetic field lines or electric field lines coming outside. Means, if you see this is closed object, if 3 lines are going like this, then 3 lines will come out like this. Like if one pencil is going like this, then this pencil will also come from outside. This is Gauss law. Okay, for a closed surface, the number of lines leaving the surface is equal to the number of lines entering. Okay, this is the main point. Okay, but now we will talk about this law in electrostatics and magnetism. You know, in electrostatics, what do we know in electrostatics? What do you know? We know that there can be in electricity there are 2 poles, plus Q, minus Q, and they are different. Whereas in magnet, it's one, north and south. They can't be different. So if I keep this charge plus Q like this inside, we know this plus charge will go out, right? So is there anti coming in? No, but it's going out. So this is a conception in Gauss law. Whereas in a magnet, if we keep like this, right, north south, this will go down, but the same lines will come, right? What I mean is, if this is north, this is south, and this, if from north the lines are leaving like this, and from south it will come back, right? So the same lines are joining and coming. So the misconception or the difference between electricity or electrostatic and magnetism in Gauss law is that there can be, for a closed surface, there can be outward flux which is not equal to inside flux when we keep a charge inside the object. Okay, there is a net outward flux since it does include a negative positive charge. Okay, there can be, okay, but it is not same for magnetic field lines. So here it says the magnetic field lines leaving the surface is balanced by the magnetic field lines entering. So the net magnetic flux is 0. Means if this book, the number of field lines coming inside and the coming outside will be equal for magnetism 100% accurately. Whereas for current, if I keep the current like this, I mean if this is positive charge, is anti coming here? No, but this positive is going out. There's a difference. Okay. And then here it says the formula that for this is for electric field, the Gauss law is E dot delta S means total field lines entering multiplied by surface, the surface area is equal to Q by E naught, whereas over here is equal to 0. That's it. Okay, so the Gauss law of magnetism is the net magnetic flux through any closed surface is 0. That's it. That's all about this topic. There's nothing about this mode. Now we will do the Earth's magnetism. So this is kind of a theory part. So like you need to learn this. I mean, this is about the history of Earth. Okay, basically it's not much even. So in this we start with the main thing, the value of Earth's magnetic field. The value of Earth's magnetic field is 10 raised to minus 5 Tesla. Okay, this magnetic field is so less, right? It's so less, right? That's why we cannot experience that much. Okay, like in our day-to-day lives, can we experience that much magnetic field lines or like magnetic power around us? No, we cannot. Why? Because it's almost just very less, just very less. Okay, and then this is about the first paragraph, and then this is about the history of, like, we know Earth conducts Earth conducts magnetic object, means Earth also has magnet and it has magnetic field lines, because of which there are many objects attracted towards Earth, like asteroids, like even the iron compositions are there, and we do experience magnetic field around Earth. So how do this Earth, or why do this Earth has magnetic field? This Earth has magnetic field, like why? So scientists want to find out. So like, I mean, like, of course they couldn't find out that much. Like, we still don't know what's the reason behind Earth's magnetic field. Like, why do Earth have this magnetic field? Why is Earth having strong magnetic field or weak magnetic field? We have no idea about that. But assuming scientists, they proposed two theories. Okay, one theory was that, like, there was just one long bar magnet inside. What they mean is that, example, this is Earth. The mean is we just kept one long magnetic rod inside. Because of this, the field lines are coming and field lines are going, and everyone is experiencing. But this is practically not basically true. We just know, because if we are digging, can't we just find, right? If we are digging to the center of the core of the Earth, then why can't we see any rod-like object? Okay. And the second was, there is a concept called Curie's temperature concept. Okay, so Curie's temperature concept, this said, look, the thing about objects which are attracted to magnets is that the magnets have a specific temperature at which they attract. Okay, all magnets have a temperature where they can attract. Above that temperature, they will lose what they will lose? They will lose the ability to attract. Okay, so all magnets will basically have the ability to not attract anymore when the temperature is high. So we know in Earth's core, temperature is very high. Then how can this magnet still behave like a magnet? It can't. It's impossible. So this theory was rejected. Second was, like Earth has magnetic molten. Okay, magnetic molten like this. What is molten? Lava. Okay. So the Earth have magnetic molten inside the, not magnetic, like they have molten lava, metal molten. Metals have what? What do metals have? Electrons. Okay, so this is molten content, molten substance in Earth's core, right? So what does this molten substance have? They consist of metals, right? Metals have electrons, right? So we know Earth rotates on its axis. Right? So if the Earth rotates, then molten also rotates. Okay, if Earth rotates, then molten also rotates, we know. And if molten rotates, electrons also rotate, right? Okay, so they also rotate. So now metals have electrons and molten is rotating, so the electrons are rotating. So when electrons are rotating, what is, they're flowing. Okay, means electrons are flowing. What does this means? This results in, what is flow of electron? Flow of electron is current. Okay, means current is produced. Now listen, current produced means magnetic field is produced. Now you understand something? Earth have molten substance in the Earth's core. Okay, these have metals. These metals have electrons. Okay, finished. Now we know Earth rotates on its axis, right? When it orbits around the sun, it rotates on its axis, and with high speed also, we know that. But we feel less because we are on it. Okay, and if Earth rotates, the electrons also rotate. When the electrons rotate, electrons are basically in motion. In motion means they are flowing. Means the current is produced. Means the magnetic field is produced. So hypothetically, scientists believe this theory. Okay, we still don't know if this theory is correct, but this is what they actually believe. Okay, so this is basically called the dynamo effect. Okay, this is called the dynamo effect. Okay, and you can read this and then you will understand it. Okay, about this. Okay, and now by experiments, by compasses and all, we also found that the location of North Pole, okay, the location at North Pole on Earth, okay, on Earth is at North Canada, and the South Pole is at Antarctica. Okay, now we are like, what is north, what is south? Okay, so this is Earth, right? This is Earth, and this is on its axis of Earth, right? So one cool thing is that you think the Earth's magnetic field is like this, like it's going like this, coming like this, and it's like this. No, it's not. The thing is, Earth is straight like this, but the field lines are like this. Okay, the field lines are like this. Okay, the field lines are like this. Okay, I'll show you. See over here, coming, going, and rotating over here. Okay, so now this is the axis, this is the magnetic field. Okay, So this part of the earth is called North Pole. This is South Pole. And definitely this is not north, this is not south, we know that. But why we call this north? Because this is the geographical north. What is geographical north? Means the northernmost part of the earth. Okay, the northernmost part of the earth is north. Okay, so the one near to it is North Pole, and one near to south, geographical south, is called South Pole. Okay, now this is called, okay, one line, okay, one line passing through center of earth vertically is called geographical meridian. Okay, means if this is earth, one vertical line passing through the center is called geographical meridian. Okay, now the north part is called geographical north. Similarly, for south is called geographical south. So this is what geographical north, this is geographical south. So if this is metal, not metal, magnet, and the field lines are going like this, can I just basically name this as north and this as south because it's close to the north and it's close to the south? Can I? Yes? Yeah, basically yeah. So this is why this is called, okay, so this is North Pole, this is South Pole. This I call as magnetic south, or south magnetic, same thing, or magnetic north. Okay, so the pole near the geographical North Pole is called the North Magnetic Pole, and the pole geographical south is called South Magnetic Pole. Okay, now this is important. Okay, if this is earth, this is magnet, right? The thing is when we keep on compass, we know this is north, this is south. This is the thing I'm going to clear. Okay, this, this portion I said I'll clear, this portion I clear it now. When I keep one needle, this is a needle, okay, like this, and this is pointing north direction, what do you guys expect? You guys expect to point it towards south, right? Because why? Because north attracts south, right? South attracts north. But interesting thing we found is the compass actually pointed towards the north, and now we are like, what? How can north attract north? North should repel south. The north behaves like a south. Okay, this north behaves like a south pole. Okay, plus the compass was pointing towards the north, that's why also we named it north. That's the second reason why we named this north to south. Okay, so but in your mind, don't ever get confused. Okay, North Pole doesn't mean it actually is not that it attracts south. No, North Pole means the compass was pointing towards north, so we called it North Pole. Okay, but it attracts south. Okay, no, but it acts as north. Okay, it acts as south. Okay, it attracts as south. Listen, that's the thing, it attracts as south. Therefore this behaves like north, and this behaves like south. It attracts north, so it behaves like south. This behaves like north because it attracts south, and this behaves like south because it attracts north. I hope I didn't mess up. Maybe I did. Okay, fine, no worry. This behaves like south, so it attracts north. This behaves like north, so it attracts south. Simple. Now this small stuff about magnetic declination dip, and that's it. Okay, so now everywhere I'm talking about what, that north and south are actually not in one axis, that north is actually like this. That if this is the vertical axis of earth and this is the magnetic axis, I'll name this as magnetic axis of Earth. Okay, we know that this is not straight like this. There's a one. There is a distance between them. What is the distance? This angle, right? This angle is called as angle of declination. Okay, this angle is called angle of declination. Where is it? Okay, yeah. Then the angle between the true geographical north. What is true geographical north? What is true means like real geographical north, and the north shown by the compass is called as angle of magnetic declination. Now you'll be like, what compass? Leave the compass. Okay, whatever. If you put a compass, if you put on compass over here, like if it is like this, and if I keep on compass over here, it will point towards this. This is the center of the earth. What is this angle? Theta. What is this angle? This angle is declination. Okay, this is called magnetic declination, or simply declination, or the angle of declination. Okay, and okay, I read this paragraph. The vertical plane containing a long material is called geographical median. Like this earth has a center line passing through it. Vertically is geographical meridian, and the line passing through the north-south direction, is called magnetic meridian. The angle between the geographical and magnetic meridian is angle of declination. That's it. That's it. Okay, now we'll talk about dip. You need to understand dip. Okay, you need to understand dip. So about dip is also an angle. Okay, dip is also an angle, but dip is an angle between the earth and the compass. What if I place one compass over here? It is the angle between the compass and the earth. Now you'll be like, how can and compass give the angle of an earth and whatever? Okay, so we know normal compass is what, like this, right? Normal compass rotates like this, but this will take a special needle called the dip needle. This needle will also move like this, up down, also side to side. Okay, up down and side to side. So what are Earth's magnetic field lines? Like this, right. Now what if I place this compass over here? Imagine I place this compass over here. Compass, magnet, anything it can be, right? Magnet will go along the magnetic field, right? Now is it making any angle with the surface? Any angle? No. Okay, fine. No. So dip angle is equal to 0. Okay, ignore this case. Okay, now imagine I keep one needle here. Okay, now this has been attracted towards where? This side, right? Now if I join this, wait, how will I even join this? Look, I joined. What is this? The position of the magnetic field, of the magnetic compass, and this is the no. Basically. Okay, so basically what I mean is, this is the component of what? Tangent component of electric field, and if I keep one magnet over here, right, like over here, it will get pointed towards this side, right? So this angle is called angle of dip. Okay, this is called as angle of dip. So in other words, the angle of dip is the total magnetic field of the earth that makes up the surface of the earth, with the surface of the earth. Understand, with the surface of the earth. Okay, so over here, what is the surface of the earth? This way. Okay, so I can just shift towards up this side. Okay, now, and what is the direction of magnetic field? Downwards. Why? Because this is connected like this, right? What is this angle? This angle is angle of dip. Basically, in neat way, if I have to write, you see here, what is the direction of earth? This side. What is the direction of magnetic field? This side. 0 degree. Over here, what is the direction of earth? This side. What is the direction of magnetic field? What is it? Downwards. Now this is making an angle. What is this angle? Angle of dip. That's it. Okay, so the dip is the angle of the dip needle between the horizontal surface and the magnetic field. Means angle of dip is equal to angle made between magnetic field of earth and surface of earth. What surface? Horizontal surface of earth. Horizontal surface. Why? Because we just took vertical. What happened in vertical? If I keep it over here, what happened? They will get cancelled out. But over here, they won't. Exactly. Okay, that's part. That's all in this. And this is also, you can just read this part. And okay, this part is actually not much. Okay, fine. I will tell you about this part. So like, if this is the horizontal of earth, horizontal or the surface of earth, right? Horizontal or surface of earth, and this is what? Direction of magnetic field, and this is where the magnetic is kept. Magnet is kept, right? Now, what is this angle? Angle of dip, right? Now, if this one I call as BH sin theta, and this I call as B. What do you call this? This one, V sin theta. No, cos theta. Sine component. This is a sine component for theta. This is a sine component, cos component of theta. What theta? Theta means angle of dip. Okay. H means horizontal. For the horizontal, the component is BH sin theta, and for vertical it is BV cos theta. Okay. V means vertical. Okay. So now we know what is tan. Sine by cos. What is sine by cos? This angle, right? So tan theta is equal to sine theta by cos theta. So I can find angle of dip is equal to BH sin theta by BV sin theta, BEV cos theta, which is equal to angle between horizontal component and vertical component. That's it. Okay, so equal to horizontal by vertical. That's it. Component. Basically this formula only. You see, the declination, the angle of dip. Okay, with this tan, what is tan? Is E by H. This is complicated. Okay, you don't have to refer this. I'll just say it straight. Earth plane, so straight. Magnetic field is going like this because it's coming like this. So we like this. Okay. Compass is kept over here. Straight. Perfect. Now, this is horizontal surface. This is vertical. This I can, and if this is making a theta, which is angle of dip. Angle. Let me just write properly. Of dip. Then this H can I say has BH sin theta, and this I can say has BV sin cos theta. then we know what is sin theta by cos theta, tan theta, so sin theta by cos theta. So to get this angle, we can take sine of this, cos of this. That's it. Okay. Now, what did we study? What did we study about declination and dip? So now, this one important paragraph we should learn. Very, very important. It can come for one question or assertion, reason, anything. Okay. The declination, which is the angle of declination, which is the angle between north pole and magnetic pole, means the angle between geographical meridian and magnetic meridian, means the angle between the geographical the magnetic line and the vertical line of the earth. Okay. And the angle of dip, which is the angle between horizontal surface of the earth and the magnetic field of the earth, or the compass, anything, because the compass will go towards the magnetic field only, right? Yeah, basically. And the horizontal component of earth. Okay, these are known as the elements of magnetic field. This is important. This is why it's important. They'll ask you, what are the elements of earth's magnetic field? You won't know. You will write some random thing. No, it's not useful. No, the elements of earth's magnetic field is declination, angle of dip, and horizontal. Now you'll be like, you know what is declination useful? Yeah. You know what is inclination useful? I mean, it's not much use of this one, but yeah, anyways. And the horizontal component of earth. Without the horizontal component of earth, would you be able to find inclination? No. Exactly. This is why inclination is important. No, this is why horizontal is important, to find this and this both. Okay. And yeah, that's it for this video. In the next topic, I'll try to finish it in one. It will be maybe long video. I'll try to make it less. It will be about magnetization and magnetic intensity. Then it will be about properties of materials. Yeah, and types of magnets. That's it. Then over. So that's all. Study well. Thank you so much.